Right, here we go. Kinesiology 230, talking chapter 4 still. Now we're biomechanics, but we're talking about some other mechanical foundations. You may recall when we had that big list that we had to parse ourselves through, we're kind of making our way down that list. So the book makes it a point to note that the SI system, which is the System International de Units, the SI system, is the appropriate system to use. You'll see in the book that they'll go pounds, they'll go kilograms, and they'll talk about interchangeably meters to yards. And I think they could have a little better consistency in the book, but that's a whole other story. They also note that there's a difference between the kilogram as a quantity of matter versus weight. And you have to understand that, the quantity of matter that they talk about with the kilogram is different because when you look at weight is affected by the gravitational forces that are actually pulling on that quantity of matter. And so it's a little bit different. It's even different on the face of the earth in different areas where you get closer to the center of the earth, where you're further away from the center of the earth. If you were to weigh with a very sensitive scale, your quantity of matter, that kilogram, would weigh a little bit, but have a little bit different weight at altitude than it would, say, at the bottom of the ocean, taking the water out of the equation. So, they just want to get this across that it's the SI system that's important, or the one that we're using primarily. So force is defined as mechanical action or effect applied to a body that tends to produce acceleration. Now, this can include internal forces acting inside the body, right? We talked about internal and external forces, and those are forces that are acting from outside the body. They have 7 main factors that they talk about here that the effect of forces in producing, controlling, or altering human movement depends upon these factors. And these are over here to the right. I just kind of cut and pasted it right out of the book and slapped it in there for you guys to review. But it's magnitude, location, direction, duration, frequency, variability, and rate. Magnitude, how much force is applied. A location, where is it applied. The direction, and what direction is the force being applied. How long is the force being applied. How frequent. You can get an idea of what these different, these 7 things are that are on page 45 here. But, I would take a minute to just kind of make sure you're familiar with these because you'll probably see them somewhere else. So Newton's laws of motion, and we'll talk a bunch about this as we go through this chapter. First law, a body at rest or in motion will tend to remain at rest or in motion unless acted upon outside force. That's law number 1. Second law, a net force acting upon a body produces an acceleration proportional to the force according to the following equation, which is force equals mass times acceleration, or can be stated as just force equals mass times acceleration if you want to write it out. But this is sigma, if you will, sigma force. So when you look at the first law, a body will stay at rest until it's acted upon. So you have the cue ball here. Unless you hit the cue ball into the other balls, these are going to stay at rest until it's acted upon. The second law, when we look at a box on a doorstep, you go out and you pick your Amazon box up off the floor. I mean, granted, there's some acceleration as that box is being pulled down to the patio because you have gravity involved at 9.8 meters per second squared. That's a force that's pulling the box down to the ground. So when you go and pick that box up, you have to apply a force to the box that's greater than 9.8 meters per second squared times the weight of that box, or the mass of that box, right? Because what happens is you go over and you have to go pick that box up, so you have to create more force than is actually being applied to the box to pull it down to the ground. Now what happens is if you go over and you're like, great, my box of bricks are here, and you go to pick that box up and it's actually your box of maybe, I don't know, shoes, and you have 1 pair of shoes in there, you're anticipating picking up a box of bricks, so you recruit more motor units. We'll go back to kind of this the last chapter. You recruit more motor units to pick up that box, and you almost hoist that box and throw it over your head because you over-recruit, you overcompensate for what you believe is a box of bricks when it's actually just 1 pair of shoes. And you have this overcompensation effect that happens when you try to pick up something that's not what you think it is weight-wise. And then the third law, for every action, there's an equal and opposite reaction. This is a great rendering of this where you have the swimmer and the swimmer's pushing off on the wall. And so you have an equal and opposite reaction where she's pushing off the wall and it's forcing her to propel through the water. We'll take drag of the water aside, because there's a resistive force there. But you have force applied here and acceleration going in the opposite direction away from the wall. So now ground reaction force. We talk a lot when we talk with athletes, we talk about how do you create the most and generate the most power from your training and then become more efficient. So when you apply force into the ground, you get as much force out of the ground as possible. And it's about getting the greatest amount of ground reaction force. We have a YouTube video embedded in here. Let's take a look. Pause real quick. Okay, so we're into this YouTube video right now. And in this video, we talk about sprinting. If you look at, once we kind of get out here a little bit and we're doing some upright running, what you'll find is when they're sprinting, they're spending very little time on the ground. You can see it's the arch forward. The heel never touches the ground. And what they're doing is they have these, as they're sprinting, they have these exceptional mechanics. Let me get this now. Pause it right here. These exceptional mechanics where they're taking this long lever and they're applying force into the ground in a smaller contact patch. And we'll talk about this further. And then on the backside mechanics, they have a very short lever, which makes it very easy to pull that lever through. So what these athletes have is a very potent combination of a ton of athletic ability. They've created a bunch of strength through working out. They've also created the ability to generate power. And they've also done hours upon hours of technical training to learn how to apply that force in the ground to get as much yield out of the ground as possible. So in that regard, it's the equal and opposite reaction, but they're delivering force into the ground as they're running, and they're doing so under extreme conditions with a very small contact patch. So let me get out of here and we'll go back to this. So, you want to be strong enough to apply that force, but you have to be efficient enough to get as much out of the ground as possible. All right, next up. Momentum and impulse. I like this from the text. When I talk about momentum and impulse, you look at, momentum being mass times velocity. The equation itself, we get out of a straight line. We talked about the sprinter accelerating that we had in the previous picture. And now we have this picture of an ice skater down here. And you have these two skaters who are performing the same spin. And when you look at this, you have one skater who is doing their spin with their arms out and another one doing with their arms across their chest. And when they do that, there's a difference in terms of the angular velocity. Now, angular velocity is how fast the person is spinning. The angular momentum includes the speed, the spin itself, how fast they're spinning, but it also includes the mass. So if you have two figure skaters performing the same spin, the heavier one will have a greater angular velocity. If you have two figure skaters performing the same spin and are the same weight, the one spinning faster will have greater angular velocity. So, it's kind of a combo platter between those two, but it's the same mass. The same math that you have. And I'm going to get these out of here, the picture of sprinter and picture of the video, because I already embedded those in. You have this ability to kind of visualize this now, look at like these long levers spinning and how that's going to change the angular velocity. As soon as she brings her arms in across her chest, she'll be spinning a lot faster. Okay, so we look at transfer momentum. With the transfer momentum, almost all sports require some type of transfer momentum. Basketball players have to shoot a ball, pitchers have to throw a ball. Wrestling, it's a little bit different because these two guys down here, as soon as they, lock up, they share a center of gravity, even though they each have their own COG, but as soon as they hold on to each other, they share it and they're trying to impart momentum into the other person, just destabilize them off of their own equilibrium point. And you'll have to have the ability as an athlete to overcome inertia. You have to have the ability to impart an impulse into the other object, whether it's the pitcher throwing a baseball up here or it's the wrestler throwing his opponent on the mat. Take your pick. So from a coaching standpoint, you want your athletes to be fully aware and understand that acceleration is kind of key. Speed is great. Top speed running is fantastic, but you have to work on acceleration, whether it's throwing the ball or accelerating your hips to throw your opponent. So when you look at this, like, okay, with inertia itself, and how would you actually overcome this when you have these different rules? Body at rest or in motion will tend to remain at rest or in motion unless acted upon by an outside force. That's first law. You look at the ability to throw a ball or the imparting of one's will, if you will, in another person's COG and trying to basically throw them on the mat, you're talking about how do you overcome that initial inertia? How do you overcome the ball not moving? You have to apply enough force into the ball to get it to move at 100 miles an hour. You have to apply enough force into your opponent to be able to throw them on the mat. I can't stress this enough. But it comes down to their ability to be strong enough to do that, their ability to be strong enough to do that here, and also the technical component to be able to be proficient in doing that as well. All right, guys, I'm going to branch out here. I'm going to fix that one slide and moving on to the next presentation.